So I think I've got this kind of sorted, so that perhaps my handwriting might be a bit more legible and this more reasonable. So all we want to do today, we're recording this, we'll put it online after the fact. We'll just go quickly over what we talked about last time to kind of rediscover exactly what we learned last time, and then we'll try and apply that to develop the conductance matrices for triangle elements. It's relatively straightforward, quick example, and then if we get to it, we'll try running that example on in our simple program. So by way of, let's see, so this is full screen, I guess. This is about as large as it can go. So just to recap what we talked about last time. So I think this should work. Okay. Recapitulate is a full word. And so what do we remember? Well, we remember that if we had any particular element type we wanted, we could define a relationship which allowed us to link nodal values of fluxes to nodal values of heads, and we did that through a conductance matrix. And so our innovation last time, if you like, was that we could derive this conductance matrix for this diffusion problem, or so it's a flow / diffusion problem. In other words, so when we talk about diffusion, we talk about fluid flow and pressure diffusion. So it's actually the same equation as Fickian diffusion, but let's not worry about that for now. And we could always figure out that this conductance matrix was always given in this form. It was an integral of two different matrices over a volume, and these two different matrices always had the same form. One was what we referred to running out of space. So the A matrix was equal to the derivative of our shape function matrix, and our shape function matrix, so these are both underlined, and our shape function matrix was something that linked magnitudes of nodal heads to the head of the point. So this is what is embodied in here. And so what it looked like for us was that it was something like the head at some point is equal to 1 minus location times the head at node 1 plus the head at node 2. That's what we used in our very simple. So for any of these situations, we can come up with another matrix which is appropriate for this. So it'll be a different. We said this is going to be. So this depends on two things. One is dimensionality. So it matters whether it's 1D or 2D, or 3D. And it also matters on the element shape. And nodes. So we had the example last time, triangle element, a node in each corner, you get a certain weighting function, mapping term matrix, shape function matrix. If you add mid-side nodes onto that, you change it. And so we talked about that last time. And so that's we can always figure out exactly what this matrix is. So in other words, in our case, this term here would be B1, and this term here would be B2. And so if you wanted to write that set in longhand, it would be B1, B2, multiplied through by H1, H2. Nothing more than that. We did that last time. So the derivative of this is just the derivatives of these functions with respect to x in our particular case. And the other matrix that we have was our constitutive matrix. So what is that? That is equal to flow velocity is equal to dH. These are the nodal values of heads. Is that right? That's not right, is it? Yeah, so it would be this. Gradients of head. And this is just Darcy's law. So in other words, in our particular case, D was just equal to hydraulic conductivity, and it was a 1-by-1 matrix with value 1, nothing more than that. And so the significance of what we've managed to do is that we came up with this relationship, and this is universal. It's always true for flow problems. It will just be that the component magnitudes of these A and D matrices change to be able to reflect our system. And so what we'll do today is we'll take the next step, and instead of looking at this one-dimensional brick with a node at each end, we'll look at a two-dimensional element that has 3 vertices, a node at each corner, and develop the appropriate K matrix for that. So that's our task for today. So anyway, so you'll see that. So this is, I've started changing these things each day. I upload this new version. I uploaded it an hour ago. Perhaps not very helpful to you if you've already downloaded it and using something else. But what we'll attempt to do today, I guess I can probably make this full screen, right, is to go through this. So we'll develop the expressions we need to represent these triangular elements. Wow, that's a straight line. That was done with my finger on the trackpad. I'm impressed with myself. Okay. So this is the idea. So we're going from an element that had 2 nodes to one that has 3. It has a node at each end. We mentioned before the fact that when we number these things, these are just numbered sequentially I, J, and M. I guess K not because it's confusing with hydraulic conductivity. It can have hydraulic conductivities of different magnitudes in different directions. We won't actually do that in this case, but that certainly can be the case. And we know that in this we'll prescribe variables in each of the nodes. And so for this particular problem, we can either prescribe a flow rate at the node, Q value, or a head. And if we prescribe one of them, then we'll solve for the other one. That's what we're attempting to do. So those are the two values. And those are kind of embodied within Darcy's law. Q is equal to K delta H. So flow rate is related to head through some magnitude. Global coordinate system, X and Y. We have nodes of these coordinates defined in terms of X and Y at node I, J, and M. Numbered counterclockwise so that we can do the calculation of the volume very straightforwardly. And so what we need to do is be able to figure out exactly how we get each of these 2 parameters that we need. And so it's moderately straightforward. This is the relationship that we want to be able to evaluate. So if we can get the magnitudes of each of these terms, A and D, then we have a fighting chance of being able to figure out exactly what that is. So first, constitutive relationship is the D matrix, right? Darcy's law. And so instead of being a 1-by-1 matrix as we had before, it's now 2-by-2. It has conductance magnitudes in the 4 directions, which we can calculate if it happens to have different conductivities in X and Y. if the directions of permeability are aligned parallel to the maximum coordinate directions, then the off-diagonal terms will be equal to 0, because those will be principal permeabilities. And if the, principal hydraulic conductivities. And if the hydraulic conductivities are the same in x and y, then kxx and kyy will be the same. And so it'll just be, you could also rewrite this in that particular case, I suppose, as a hydraulic conductivity multiplied by 1, 0, 0, 1, right, in that particular case. So that's the simplest case that we can deal with. So this is isotropic. So that's the normal case, but you certainly can deal with it in those other cases. Well, this is it. And so physically what this constitutive relationship is it's Darcy's law. It says that if you apply a gradient of head in the x and the y directions, then you get velocities at that point defined in each of those two directions as well, and of a particular magnitude. So in short form, this is velocities being related to head gradients through this matrix. And so we've defined that. So the D matrix is just a 2x2 matrix in this particular case that links gradients and head and velocities, and that's done. So that leaves the second component. And so we'll do that in a slightly different way. So last time we said, or this time as well, we said that the gradients of heads are equal to the A matrix multiplied by H. And so if we want to get that, then we can get the magnitude of the A matrix as being equal to the derivative of the shape function matrix. So these are both just the derivatives of those. And so we could do that here, but we'll do something slightly different. And that is that what we'll do is that instead of defining the shape functions as we suggested before, and so before we suggested that we could always get the shape functions to get the magnitude of the nodal variable at a point as a function of some function, shape function, times the nodal values of the heads. We can do that again, but we'll do it in a slightly different way. We won't define shape functions in this particular way. We'll revert to the fact that if you go back to this, and if you think about this triangle as having a head magnitude, which is the distance out of the board to here, and a head magnitude of this location, which is the distance out of the board to here, and likewise for this, those 3 points, the elevations of those 3 points can be met by a plane which passes through all of them. That plane is a surface that goes on top of this, and the equation of that surface will be something like this. It'll be a constant magnitude. That'll be the magnitude, the height of that surface at x equals 0, y equals 0, plus gradients of how that surface changes as you go in the x direction for this term, and as you go in the y direction. And so those aren't quite shape functions, but it is a way of us being able to say how, for instance, if we know the values of heads at a particular point, we should be able to map those into the particular magnitude of head at any single location here. So what we'd like would be a magnitude of head to be equal to some function times the magnitude of head at node I plus some function, I guess I should call these j, plus some function m hm. So these values we'll have because those will be our nodal variables, and we have to figure out exactly what these components should be. So that's our job. But instead of doing it the same way as we did for the two-dimensional element, we'll do it slightly differently. We'll take the fact that we can define the magnitude of the head at any point as a function of this surface, which is the equation for the head surface above this element. Certainly we can take the derivative of this. If we differentiate with respect to x, we just end up with this term drops out, this term drops out, and we end up with just b, which is this. If we differentiate this expression with respect to y, the only term we're left with is this. So a constant times, well, 1 times c, and the other terms drop out, so we end up with this. And so we can certainly get the gradients of those magnitudes, which will be of use to us. And it's of use to us because this is basically what we want that acts on the constitutive relationship we have. So what we can do is we can write the magnitudes of the heads at any point as a function of this equation. So if you take on trust, or if you believe that this is the expression of the surface that represents the head, then certainly we can write that 3 different times at 3 different locations. We can write it when it's at the bottom left-hand point on our figure, right? We can write it at this point, and at this point the coordinates have to be x, I, and yi, and the magnitude of this head is hi. And so we could write this expression in terms of that. This is the location where that head is applied. This is the magnitude of the head, and we have 3 unknowns, a, b, and c we don't know. This b value, by the way, is not the same as our shape function that we're talking about here. So just take that on trust. If you write it at the second node, it'll be at locations of the x and y coordinates of that second node, and it'll be whatever the head is at that number. And likewise for the third node, that'll be the same. So we have 3 equations. We have 3 known coordinates in x, 3 known coordinates in y, 3 heads, but we have magnitudes of a, b, and c which we don't know. And so we could just write that as a straightforward relationship which links those. So equation 6 is nothing different than equation 5, but just written slightly differently, so that we isolate these values that we don't know yet. And so what we could do is then we can invert this equation to get the values of a, b, and c as a function of these nodal values and as a function of the geometry of the element, right? This only contains properties which are a function of the element. And so if we can invert that, we end up with magnitudes of a, b, and c, for which we need some of them anyway, as a function of nodes and also as a function of these coefficients which are standard results. And I think in here you have, I won't go through it, but you get the standard results from just inverting a matrix. It's the inverse of the matrix is just the adjunct of the matrix divided by the determinant. And so it looks like this. And so it's just a straightforward matrix of, again, the matrix starts off with only the geometry in it. And so the inverse of that can only contain the geometry as well. So these are just the coordinates of the nodes arranged in some way. And 1 over the determinant is just equal to the 2 times the area of the element, as it turns out. And so we won't go through that. But the main point is that as a function of inverting this matrix here, we get a standard result, which gives us, these are just xy coordinates. This is 1 over 2 times the area of the triangle as a standard result. And it allows us to be able to calculate 2 magnitudes. Calculate the magnitude of this coefficient b and this coefficient c. And those are of use because those are the derivatives of this expression. And so what we're interested in getting is a magnitude of the derivatives of these. No, we're interested in two properties. We're interested in the derivatives of the heads in the x direction and the derivatives of the heads in the y direction. And we can get those if we know the magnitudes of this coefficient b. And so what we can use once we have these is we can get the magnitudes of the values of a and b just from this expression, right? So what's it going to be? The magnitude of b is going to be equal to 1 over 2 times the area of the triangle multiplied by this times this plus this times this plus this times this, right? So it's just going to be equal to A21 multiplied by HI plus A22 multiplied through by HJ plus A23 multiplied by HM. And this is going to be equal to the change in gradient as we go in the x direction. And so if you look down here, that's exactly what we have. We have the gradient in the x direction defined as b, which is just the product of these terms multiplied by the nodal heads. And likewise, the values of gradients in the y direction are just the values of c from this above here, this result, this here. And again, are just geometric terms which relate to the geometry of the element. So all of these terms are merely terms that represent the element. So if you like, by definition, we've skirted the need to be able to develop the conductance matrix, because if you like, we've gone back to our, oops, can't have that there. We made this point, actually that's right, so this is, so what we didn't put in here was that the gradients of head, dh dx, is equal to AH. And so if we're able to get the magnitudes of these nodal heads, apply them, and get the gradients of those through some operator, then de facto we've figured out exactly what this A matrix is, which is this one that we're interested in figuring out. And so in one dimension we link heads with gradients in the x direction. In 2 dimensions we link heads with gradients of heads in the x and the y directions. And so if we go back to the expression that we have on this page, we basically have that, right? We have a gradient in the x, gradient in the y, linked to nodal values of heads. So by definition, this really is this A matrix. That's what we did. So we circumvented it. We didn't describe shape functions, which we then differentiated. Instead, we tried to get a relationship between gradients of head and nodal heads. And this, by definition, is that. And so, if we have the A matrix, we have this. We've already said exactly what we had before in terms of this conductance matrix. So we have everything we need to be able to put this thing together. Okay. What are the sizes of these things? Well, they have to make sense in terms of size. So the size of this is going to be 2 by 2, right? D matrix. What's the size of the A matrix if we do this in rows by columns? So the number of rows we have are 2, right? This is 2 by 3. So this 2 and this 2 have to be matched, otherwise we can't multiply them together. And likewise, when we look at this is going to be, in size, it's going to be transposed. So this is going to be 3 by 2. And again, when you multiply these things together, they have to have the same dimension, otherwise you can't physically multiply them together. So this is our general form for this. We know this is our A matrix, which we have. X and Y coordinates, the area of the triangle, standard result, let's not worry about it. We have magnitudes for our K matrix, which would be however we want to describe it, either as isotropic or a bit more complicated than that. And we just put those things together here. There are a couple of other things that we can also manipulate before we go there, though. What do we notice about each of these matrices? Well, the D matrix is a function of material properties. So long as conductivity doesn't change with location in the element, it can change in orientation. It can be different in the x or the y direction, but as long as it doesn't change with location in the element, it's constant. So the D matrix is constant, just numbers. Likewise, the A matrix, we didn't really, did we zoom past? This A matrix will be a function of x and y coordinates of the nodes. Not of any place within the element, just of the nodes. So for any given element, those nodal coordinates are one value and one value only. So those don't change either. And so the two matrices that we have are constant in space. So since both A and D are constant in space, we can take this integral and we can take them outside that integral. That's what we're doing here. These are constants, so we're just multiplying by a constant. It happens to be a matrix equation. It's going to be the magnitude of the outside terms, so this is going to be 3 by 3 in size. if you look at this term here and this term here. That's the way it has to work out. And the integral is just the integral over the volume. And so what's an integral over volume of a triangle is just going to be the area of the triangle times its thickness. So I don't know what term we want to use for thickness. Maybe W is better, and has an area. So the volume is equal to the integral dV, which is equal to, whoops, area, right? So by definition, that's all it is. And so if this is just the thickness times the area, so this is just the volume, then all of a sudden it just becomes a matrix relationship, and we don't need to do anything with the integral. The integral has just disappeared, magically disappeared. So part of the reason for that explanation, of course, is that the other way to interpret this is that these A matrices, they represent, if you like, they define a gradient. They take nodal values of heads, which are constant and only defined at the nodes, those three nodes, and they multiply it by some number and get a gradient. Because these are constants, then it means that the gradient of head has to be constant everywhere in the element. And so we didn't say it at the time, but define this as a constant gradient element. Physically, it means that because, makes sense, right? Because we're taking this distribution of heads, some magnitude of head here, a smaller one here, maybe 0, it conforms to a plane that goes above this. If you take the derivative of that with respect to x and y, the plane, by definition, has to have a constant gradient in x and a constant gradient in y for this plane.
So imagine we have two triangles, one next to the other, and there is one sharing node. If we have a constant gradient where in different elements we may have a changing gradient, would that mean that the same node has two gradients?
The element would have two different gradients as you go across it. And so let me draw it on here, what I think you're talking about. So the question is, if you have an element here, and if you have an element here, and you draw a section across here, then you can potentially have two different gradients, and that's exactly right, right? So if we drew this pressure, can't draw it very well, you could have a gradient in this element that's here, and it could change to some magnitude as it goes here, if this is pressure versus location. So you can have different gradients in different elements, but what we have to make sure of is that we have continuity of flow across here. So the gradient doesn't have to be constant across there, but what it does have to satisfy is it satisfies mass in equals mass out. So, and that will be satisfied. I'm not sure we'll necessarily show that, but that will be satisfied. So they don't have to have the same gradients. Of course, if they had to have the same gradients, you prescribe the behavior in your whole system. So yeah, so they don't need to be the same. So yeah, good question. And so because this is the equation of a plane, if you look at whatever orientation it is, take it in the x direction, it has a single gradient everywhere as you look in that direction. If you look in the y direction, the slope of this relative to that plane has to be the same in the y direction everywhere. And so it's not surprising that we're calling these a constant gradient elements, and so on. So, how do we do that? Well, I didn't mention the standard result, but you have the standard result here, is that if you take the inverse of this matrix, these are just the coordinates of the j, m, and I nodes, which we can get. And so we can actually prescribe the magnitudes of this. So, it turns out, of course, in this, that we don't care about these top ones, right? These ones we don't care about, because we're only interested in these two values, B and C, which go into here, right? And so really our conductance, our A matrix is actually this part here. These terms. So this is the A matrix, inclusive of this 1 over the determinant value. and the determinant is just, again, a standard result from that. Okay? So it's really just a number that we apply. You can look at that for details if you wish. And then what do? Well, once we have these, we use the same idea of indexing this as we did before. And the idea of indexing is that we can take this network of triangles and we can just pull one out at a time, and we can directly use this expression to be able to figure out exactly what the conductance matrix is for that particular element, and then we can use it in some way to put it in a global system to be able to ultimately solve with it. You go to the next element, you repeat that. So that's really all we're doing in all of this. And so, let me just check with this. Yeah, okay. So here's an illustration. What do? So what we do is we use this expression to be able to get this conductance matrix. We do it first for maybe the first element here. We know that if we number these things as local nodes 1, 2, and 3, then we'll get a conductance matrix that will be defined in terms of those local nodes. And in this particular case, local node 1, and so there's a difference between the global numbering. So this is a network of 1, 2, 3, 4, 5 nodes and 3 elements. It has local node numbers, these bracketed terms, but it also has global ones. So the global ones are unique. 1, 2, 3, 4, 5, if we had more, 6, 7, 8 to n, so they never repeat. But the local ones, as you remember, are really just the template that we're going to use. And the only important thing about the template is that it has a node 1, it has a node 2. We call them I, J, and M, but we can also just number them sequentially, same idea. And we take this template and we put it over here. And so when we define this in terms of local node numbers, this is our local node 1, local node 2, local node 3. And those also correspond to these global numbers. So exactly the same as each other. And so, bless you. And so when you look at numbering the nodal degrees of freedom, which are global numbers, and linking fluxes to heads, then the conductance matrix we calculate just from applying this will directly give us the right terms in this matrix, and we'll know what to do with them, because when we write the global matrix, which is what this would be, is that we want to link the behavior we have at nodes 1, 2, and 3 globally, and fluxes 1, 2, and 3 globally. So the terms that go into this portion of this matrix will be the ones from the first element. And so the first element terms are this, and this, and this, just directly dropped in there. So indexing between the local node numbers and the global node numbers is important because it allows us, without thinking, to be able to put the terms in the right location. And so that's what we're doing here. So these are so we use K is equal to A transpose D A area of the triangle times thickness. We use this to get this element here. We number these in the appropriate location, just according to our scheme. We always do it counterclockwise. See, 1, 2, 3. It doesn't matter whether this one is 1 and this one 2 and 1, 3, but it does matter that they be counterclockwise, because the area from this matrix relationship, from the determinant, is negative if you do it the other way around. And we just need to make sure that we number the rows and columns accordingly so that these correct terms go into the right place here. And so that's the ones we've done. So it gets a bit more difficult, well, not more difficult, but you have to use the same system when we look at element number 2. So element number 2. we're going to number this. This is going to be node 1, 2, and 3, but this relates to global node 2, 4, and 3. And so that's exactly the numbers you see here. Global node 2, 4, and 3 represent those. And so if you apply this, this relationship again to fill out this matrix, you end up with these terms. And I've just numbered them this way so you know where they go. They go into the global matrix according to this. So let me make it smaller. Maybe we get both on at the same time. I'm not sure we can. Some stage that goes side, the one actually goes, can you see that? And so these ones will go row 2, column 2. So this will be one that goes here. They'll go row 2, I guess row 4, column 2. This one here. And row 4, column 2, row 3. It will also go here. So they switch around. So it hasn't been this block of 3 by 3 that physically goes in the same location. Now they're juggled around. And likewise, if you look at this, in the 4th column here, you'll have this term which will go here. You'll have this term which will go in 4, 4, which should be right here. Can't see if it quite is, even on my screen. And this term which will go in column 4, location 3, and so on. And so all that matters is that you do the indexing in the right way. And then again, just to confirm, you repeat for the same one for the third element. So in this particular case, the local node 1 is global 4. So this would be 4. Local node 2 is 5. And local node 3 is also 3. And so when you have that, then you just follow the numbers. So you'll see that these numbers that we've given it here as these subscripts are just the appropriate number for the row number and the column number to go here. And then it just becomes it's an indexing method that's used to do this. And so once you have those all put together, you have a global conductance matrix linking all of the fluxes at the nodes to all of the heads. You apply boundary conditions in some way, and you attempt to solve it. That's it. So that's really what it is. So it all revolves around being able to do that. Always, I try and give a quick example of doing that. I guess we can do that here. I mean, it's pretty straightforward to do, just to work through it. And so what I propose to do today, let's go through just a simple calculation to figure out exactly what the magnitudes of those terms are that go into that matrix. And let's try and use it in an example to solve for a problem, both by hand, if you like, and also using this EGFEM code. Okay, so if everyone's okay with the indexing idea, we can move ahead. So this is the deal. So, simple example. So you have an element. It's of this geometry, this size. It's 1 in length on one side, 2 in length on the other side, a right-angled triangle. It doesn't matter if this is 0.00 or if it's translated to 100, 100, and the relative size of the element is still the same, 1 high and 2 wide. The conductance matrix would be exactly the same, even if it's translated through that. We want to be able to calculate the conductance matrix, which we know is A transpose dA times the area of the triangle and its thickness. We know that the A matrix is equal to these components, as you recall. We just scoot back here. It's just the bottom part of this chart. And we didn't really spend any time dwelling on it, but it's these terms individually. So perhaps it's easier for me to do it and work out what these terms are here. Let me just draw our figure. Was this node 1? I think it was, right? I think it's 1, 2, 3. Counterclockwise, has to be. Yeah, IJM, so 1, 2, 3. And so let's put the coordinates on it. So what this was 0, 0. This was, 2, 0. And this was 0, 1. For x3, y3, right, etc. And so what are these magnitudes just for this? So it'll go in here. So y2, so x, which is 0, minus y3, which is 1. So this, I think, should be minus 1. This is y3 minus yi, so y3 is 1 minus 0 equal to plus 1. Yi is 0 minus yj, so I think this is 0. And the x-coordinates. X-coordinate of ij, x-coordinate of 3 is 0 minus x-coordinate of 2 minus 2. You should correct me if I'm wrong. I'm often wrong. X1, which is 0, minus x3, which I think is also 0. And x2, which is 2, minus any other x, which is 0, should be 2. So those are the terms. You might remember that this term here is 1 over the determinant, but it's also 1 over 2 times the area of the triangle. So the area of the triangle is 2 by 1, so it's a half. So the area of this triangle, 2 by 1 would be 2 total, so it's half of that is equal to 1. So this delta is equal to 1. So I think, I'm going to go out on a limb here, I think our A matrix should be 1 over 2 multiplied by the terms that are in here. And it should be minus 1, 1, 0, minus 2, 0, 2. See if that actually is the case. So 1, can I do it so small that we can see both at the same time? No, can't. Let's go. Minus 1, 1, 0. Well, it can be larger, I guess. Minus 1, 1, 0, the top row. Minus 1, 1, 0, that's right. Minus 2, 0, 2. Minus 2, 0, 2. Yeah, I can actually do something, so it's good. And so this term here is exactly what we have from this. This is equal to 1, the area of the triangle. You can also do it by the nodal coordinates. As I say, the only reason for numbering this always counterclockwise is because it gives you this area is positive. Delta comes out being positive. If you number it the other way, then you just have to make a correction because it'll come out negative. That's the only reason. So, we know what the A matrix is. What's the constitutive matrix? This is, if the conductivity is 1.0 meters a second, then this is just equal to that. So this is in meters per second. The units of this are in what? These are lengths minus lengths, so they're lengths divided by an area. So I guess the units of A must be 1 over meters in terms of dimensions. It's always useful to follow that. The other thing to mention is that, we mentioned that most finite element codes not only allow you to do 1, 2, or 3 dimensional problems in the same code miraculously, It's because of this indexing, but also they never prescribe, they usually don't prescribe material properties. So your units just have to be dimensionally consistent. So you need to choose a unit for length, meters, a unit for mass, kilograms, and a unit for time, which is seconds. As long as you are consistent with that, you'll be fine. All right, so the K matrix is just these products. So we have this A matrix. I guess it actually includes this as well, right? This is D, and this is A transposed, and this is area. I guess it should have a thickness as well, but we don't. The thickness is always the same, we don't care. And if you multiply these out by first multiplying this by this, and then this by this, you end up with this matrix. And so this is just a quarter, and the magnitudes of these are just defined in terms of this multiplication. And you notice a couple of interesting things. One is that you notice that this conductance matrix has only positive terms on the leading diagonal. It will always only ever have positive terms on the leading diagonal. So it's positive definite. So positive definite means, if you've never heard the term, so definite means it is not equal to 0. So it won't have 0 terms on the leading diagonal, and they'll always be greater than 0. They'll always be positive. They won't be negative. And the other thing is it's symmetric. So if you look around this leading diagonal, it's symmetric about this. And the other thing, I guess, that you'd note would be that the terms on any line or column all sum to 0. And the reason that you can figure that why that might be is that if you write this expression in longhand, yeah. Well, I guess the reason is if you do we have it written out here? That's what we're going to do. The reason for that are that if you write this expression out in longhand, and you set it equal to H1, H2, H3. So in this particular case you have 5, -1, and -4. So if you think about physically taking this element and you put a head of 1 at each node, what is the flux that should come out of node 1 or any of the nodes for that matter? Yeah. 0 gradient. Darcy's law says that flux is related to gradient. If the gradient is 0, then the flow through the element must be 0 as well. And so if you put 1, 1, 1 here and multiply 1 times 5 minus 1 times minus 1, 1 times 4, then by definition it'll give you a 0 flux. Likewise for the other rows as well. And so it's always a characteristic outcome of this is that individually the element matrices must be positive definite and all the terms must sum to 0 on the rows, and since it's symmetric then they also sum to 0 on the columns, and the reason for that is what we just said. And once you put them all together and assemble them into a global matrix, the same has to be true as well. All of the terms on the rows have to sum to 0. And so, yeah. So. And if we wanted to solve a problem using it, then we can just go ahead and do this. So this is kind of a hand-worked problem. So the geometry we're going to have is going to be flow in a prism with an upstream head of 1, a downstream head of 0. It's 2 meters long, 1 meter across, 1 meter into the page if you like. We're going to think of it as 2 elements. The first element we've done as being 1, 2, and locally 3, right? But we can define it by 2 elements. These are the global node numbers, 1, 2, 3, and 4. In the particular case that we did before, the local numbers would be 1, 2, and 3. So I guess we could put that on here if we wanted to. This would be 1, this would be 2, and this would be 3. And so in other words, this transformation between local and global numbers that we have for this is the element that we just got, right? 1, 4, this. Local node 1 is global node 1. This is local node 2 is global node 2. But local node 3, which is this column, whoops. Local node 3, which is the last column, is global node 4. And so the indexing that we'll ultimately use is going to be this. So these are the global numbers to find. You can do the same for the second element. Actually, you'll realize that this happens to be the terms for the second element. You can actually get them from the first element just by induction, because it's the same geometry just turned upside down. I won't try and do that here because I'm sure I can't. But you'll notice for sure, if you get the magnitudes of the parameters in here, you'll notice them, they're 5s and 4s and 1s. 5s and 4s and 1s. And they're just juggled around based on the numbers. And so these are the particular global node numbers that relate to that particular case. And so now we want to be able to put together the global conductance matrix, which is this. And it will look like this, right? We have 4 nodal degrees of freedom for fluxes. We have 4 nodes with heads attached to them, and they're linked to some matrix which has to be 4 by 4. And so if now we number the global nodes as 1, 2, 3, and 4, 1, 2, 3, and 4, then we can just take the appropriate magnitudes out of this matrix. So 1, 1 is 5. 1, 2 is -1. And 1, 4 is -4. So you see immediately where those go. The other terms that we have will be, this will be in the first column, but row number 2. So this is here. And this term, because it's 1, 4, will go there. Nothing more. So we're using this indexing to do that. And we know that the other terms are going to be this just by looking at where the patterns are. So those will be the other terms that we have. So that's everything for this matrix. I've never got the colors to work on this. Too difficult to figure out now. Use a different symbol. So I'll do circles for this. So this is 2, 2. And so 2, 2 is this one here. Row would be 2, 3. So that's this term here. And interestingly enough, some of the terms are null. They're 0, but they're not null. And this would be this term here. And so you just go through it like that. And so once you've done that, then you apply, you have a conductance matrix. So once we have this relationship, we want to rearrange it now for the boundary conditions that we have in our particular system. And actually we don't have any undefined, I mean it's a very easy problem to solve because we don't have any undefined behaviors. We know that the heads are prescribed on this boundary here, so it interacts with these 2 downstream nodes, and also the head is prescribed on the upstream portion, so it prescribes the heads on those 2 upstream nodes. And so what we do know is we know all of these conditions. We know that if we look at the global numbers, this is 1 and 4 are 0, and 2 and 3 are 1. So 1 and 4 are 0, 2 and 3 are 1. And just in the way that we've prescribed these boundary conditions, we actually don't have anything to solve because we know all the heads, but we don't know any of the fluxes. And so here we don't actually have to do any kind of matrix inversion at all. We can just multiply this out, and it'll give us the magnitudes of these fluxes, which will be a quarter coming out of node 1, a quarter going into node 2, a quarter going into node 3 and a quarter coming out of node 4. And so if you want to be able to look at the total flux that goes into here, this is a half, right? Adding these together. And you can check that, of course, with a couple of things. You can check that the amount coming out of the system and the amount going into the system has to be the same. It's a steady state problem, so by definition it has to be satisfied. So if you add up all of these magnitudes here, you end up with no flux. And the other thing is, you can be more definitive than that. You can calculate what Darcy's law would tell you about this. Flow rate is equal to area times K times head change over length. Area is equal to 1 times 1. Hydraulic conductivity we said was equal to 1. Head drop is equal to 1. Length over which it occurs is equal to 2. So this is equal to half. And the unit's going to be area, length over time, no units, so meters cubed per second. And so that's exactly what you get. This is in 0.5 meters cubed per second. It's a volume flux that comes out of it. That's it. So that's it. So we have a single expression that says something about how we take Darcy's law and we make it into the conductance matrix for an element. We define the terms in that as a function of two things. One is the material properties, which are hydraulic conductivity, and the other is the geometry of the element, and we do that through the nodes and through the thickness. So x and y coordinates of the nodes only. And then once we do that, we get an element for each, a conductance matrix for each element. Once we have that element conductance matrix, so long as we are careful with our indexing, we can know exactly where it goes into the global matrix, and then we just do it for all the subsequent elements that we have to be able to put those in the right place. Put them in the right place, you rearrange for whatever boundary conditions you have. We didn't have any rearrangement to do here, and you solve your problem. I guess I didn't fill this in, right? Sum of this is equal to 0. So that's it. And so you can check whether it makes sense. Right? Believe everything. That's all finite element analysis is about. So let's go the next step and implement that numerically. So this little finite element program in this MATLAB code does exactly this. We used it already for our particular geometry of a one-dimensional flow system. Let's solve this exact same flow system using that. So remember what this looks like. Perhaps I'll just draw it up here so that we're all reminded of it. And in terms of the right, 1, 2, 3, 4. This, okay, not quite right, was it? And this is 2. This is 1. This is h equals 1. This is h equals 0. Yeah, that's everything we need. And so we can try and solve that problem very quickly using that code that we have. Let's see how it sets up. Can you see that at all at the back? Can you? Got better. I can barely see it from here, but that's fine. Perhaps you're just being kind. This was our program that we dealt with last time. Last time when we ran it, it just defines the data file that it takes. So all the change in this code in executing it from one to another is just change the name of the data file that it sources. And so in the terminology, 2 means two-dimensional, 1 means flow, 2 means diffusion with advection, 3 means solid mechanics, 4 means Navier-Stokes or something like that. It doesn't really matter. But this is the data file for this particular case. And so let's look at what that data file looks like to be able to solve this kind of problem. And so the data file needs to just have the right sequence of information for it to look for so it can solve any particular problem. And so the typical information that it looks for are the bare minimum, the bare essential information it needs to solve this element problem is to take a triangular node like this. This triangular node will have nodes 1, 2, and 3. It will have coordinates for those locations as well. It will have a hydraulic conductivity. It will have a thickness, I suppose. 4 is equal to 1. And that's all you need. And so what it needs to know is that it has heads or fluxes at each of these nodes. So this is 1 degree of freedom. So you'll see the shorthand in this. DOF is degree of freedom. You can see that throughout kind of finite element stuff. And so the information it needs to be able to solve this problem is just this. How many nodes are in the system? 4. And so if you look down here, that's exactly what this is. So these terms here are just these values. So number of nodes in the system. Number of elements in the system. 2. Number of degrees of freedom. So number of degrees of freedom per node, 1 head per node, 1 degree of freedom. It matters because the size of the matrices that it will make will be conditioned by that. The maximum number of nodes per element. 3. Again, it needs it to save enough space to put all this stuff. The maximum number of materials. Well, in this case, material 1 is equal to material 2, so there's really only 1 material. And so we could change that, I guess, if we wanted to being only 1, but it happens to be 2 here. I think they're both being the same. And the number of space dimensions, 2-dimensional problem. So, number of space dimensions is important because if you want to define enough storage for all of these things, the coordinates you'll have will be x and y, 2 values per node. If it's a 3-dimensional problem, it'll be x, y, z, 3 values per node. And there will also be 3 degrees of freedom typically per node as well. Actually, let's not do that. For solid mechanics problems, yes. So this sets up how much storage you need to have available to execute the code. Nodal data. Node 1, x coordinate, y coordinate. It would be z coordinate as well if there were 3 of them. So node 1, x0, y0. Well, 1, 1, I guess I did it here. So I just translated it, so this is 1, 1. So that just moves everything. If this is 1, 1, then this would be 3, 1, right? This would be 3, 2. And this would be 1, 2, I think. So global node numbers, does that make sense? First one is 1, 1. The second one, 3, 1. Third one is 3, 2. And node 4 is 1, 2. So these are just the magnitudes of the node number, x coordinate, y coordinate in each of those columns. So we have all the information of the geometry of the nodes. The elements. Well, element type is 2, 1 is this, I said. 2 means 2-dimensional. Triangular elements in this particular case. 1 means for these flow problems. That's just my little code to do that. And you then prescribe in this element subroutine what it is that the parameters are that control it. If it's a heat flow problem, it would be Fourier's thermal conductivity. If it's a diffusion problem, it would be Fick's law. But here it's just a parameter, a series of parameters. Parameter 1 is hydraulic conductivity. Element thickness we need, I guess these 2 things that I mentioned here. and capacitance. It's not a transient problem, so we don't have to worry about that. So in this particular case, for this element, material number 1, hydraulic conductivity is 1, thickness of the element is 1. The second element, okay, I'm doing this wrong. So this is the element number. It's the second row, so it knows it's the second element, second material type. It's hydraulic conductivity 1, thickness of 1, and a capacitance of 1. We don't need that. So we're defining the properties we need to define. Nothing more than that. Element association. So this is the key part. Element number 1. So this is our Roman numeral. Material number 1 gets applied in this, and we need to define what the nodes are that go with that. So the global nodes that go with nodes 1, 2, and 3 are global 1, global 2, global 4. Hopefully that's right. Global 1, global 2, global 4. We could also do this, this, and this. It doesn't matter. We would just change it. We could start here and finish there. So it could also be 2, 4, and 1. It would work just as well. Let's see if you believe me if that's the case. Let's try it. That should work just as well, I think. Nodal constraint data. Let's see, doing it slightly differently here. Yeah, okay. So, let's prescribe the problem differently. We know that the flow into here was a quarter at this one node, and quarter of this node. So we could define it in any consistent arrangement we have. Let's not complicate matters. Let's instead do it as this. So 1 means that we're going to prescribe head at that node. 0 means we're going to prescribe a flux. So let's see if this should work. So node 1, head is 0. Node 2, we prescribe a head. The magnitude of that head is 1. Node 3, we prescribe a head. The magnitude of that head is 1. And node 4, we prescribe a head, and that head is 0. And so the two key parts of this, I think, in terms of what's very specific to finite element analysis, is this indexing thing, which allows us to move from the local element to the global element automatically. Oops, I've run up against time. And the other part is defining the boundary conditions in terms of nodal values of heads. So let's actually run this thing. Let's see what we get. Let's see if it actually comes through. Let's zip through this. Even if as we zoom through this, let me just zero it and let me run it again. So it's a fresh screen. And so you'll see what we see. Even if you go through this. 4 nodes, 2 elements, 1 degree of freedom per node, 3 nodes per element, it's a triangular element, 2 materials, 2-dimensional, number of equations, we don't care. We have this information. You'll recognize some of these things. This is 5 over 4, right? 1.25, 1 over 4, 4 over 4. So this is the local stiffness element. The global element, it takes up its appropriate locations. Don't care about the damping. The next element. This is the stiffness matrix for the next element. We put it in the global matrix so that we have these appropriate terms. And then let's skip all the way to the end. These are the boundary conditions we've prescribed in terms of constraints. These are the nodal fluxes at the end. So the heads that are in here are 0 up downstream, 1 upstream, 0 downstream, and the magnitudes of flow rates are these quarters. So that's it. So we've covered a lot today, but actually we've covered 10 years of finite element analysis, all of the techniques that are used here, or what are used in CumSol, you'll never see them, they're embedded, but the mechanism is the same. And so you just need to, you localize in an element, you describe local behavior, you take that local behavior and you index it so you can put it into this global conductance matrix. Once you have that, that's the main part. The other part you do is you code your boundary conditions in a certain way so that you can just manipulate the matrices. So I'll leave that. Exciting stuff, don't you think?